Hello again, students. This is the last part of this chapter, breaking down our solids. So, a little tricky. We gotta have to think about some of these things, but we'll look at these in just a minute. Now, we'll start with here the different types of solids we will talk about. We'll break them down into these four basic types. Not too hard, but each has its own little properties. We have metallic solids. Essentially, how are metals form a solid? How do metals interact? They are ionic, so how do they form interaction and why does it give them these properties? So we'll talk about the metallic bonding, which is our free-floating sea of electrons. We have ionic solids, which is our metals plus nonmetals that are held via essentially ionic bonds. We have our covalent network solids, which are basically how do nonmetals form large molecules by sharing electrons. And molecular solids, which is essentially we have small individual molecules freezing into a solid form. And that has to do with our van der Waals attraction. But before we can really understand a solid, we need to be able to talk about solid in a few terminology. So most solids will be classified as a crystalline solid. Now, to be a crystalline solid does not mean it has to form giant crystals that we can easily see and you're like, I'm going to turn this into a gem. It means to adopt an orderly repeating pattern or geometry. So it forms a repeating structure that you can see that pattern throughout the atom. And this is a generally lower energy stable state. And so this is going to be the preferred state. However, it is possible to have a very disordered pattern, which is an amorphous solid. And these guys are usually very soft, very easy to melt, very brittle kind of things. It's not held together in any sort of... It's basically like when you have things ordered very nicely, they fit together and they take up less room and they can interact more strongly. If you just throw things in a pile, they don't necessarily fit together nearly as nicely, and so it takes up a lot more space. But so crystalline solids will have defined shapes, a very well-defined melting point, and they're usually lower in energy, so they're more stable. So we will focus mostly on crystalline solids because it's really hard to talk about amorphous solids. But one thing we need to know is we need to be able to describe a unit cell in order to describe these crystalline solids. Now, a unit cell is looking at what a unit cell is the simplest 3D repeating unit of a solid geometry. We're going to draw an imaginary crystal lattice. This crystal lattice is just a scaffolding box that we're going to use to hang our atoms on. It's not actually present. It is just there to show us where the atoms are in reference to the other atoms and how this unit cell moves around. So depending on where we draw a crystal lattice depends on what the unit cell is. Like this one is a unique pattern that we can draw multiple different unit cells and the two unit cells and imagine how this pattern goes. I could draw the lattice where the x's cross, and so as I move this up, down, left, right, you see the white spots that in the middle of each atom. I could draw the unit cell based on where those white spots are with this guy in the center. I could draw a smaller unit cell of a diamond through all of the four spots and move this down and up and left and right. Or I could draw the unit cell where all the x's cross, or the diamond with the spot. And no matter each of these guys, as I move them up, down, left, right, we will see the repetition of this shape. That's how it's supposed to work. Now in 3 dimensions, we're going to move this box up, down, left, right, front, back, and you should see a repetition of this unit cell in all directions until you reach the surface boundary of the atom, which is when it will start to differentiate. Now, there are 3 very common unit cells that will come up a lot, and they have their own terminology. We have the simple cubic, which is where we hold the lattice with the atoms only in the corners of the cube. We have a body-centered cubic, which starts with a simple lattice, and we put a single atom into the center of that cube as well. And there's face-centered cubics, where we have the simple cubic, atoms in the corner, but now we put atoms on all 6 faces right in the middle of those 4 atoms on each of the corners of that face. So it kind of looks, it makes kind of like a 5 pip on each of the face. But each of these cubes starts with 8 corners, and so it starts with 8 atoms in each of these lattice points. And so when we think of this, we got to think about there's 6 faces, there's 8 corners, there's generally 1 center of this cube. But how these atoms are counted changes, and we'll see. But so we'll start by talking about metallic solids, because they are the easiest. Since they're just metal, there's not really a matter of how they're packed. It depends a little bit, but not too much. Now, these bonds are stronger than dispersion forces, but they are weaker than covalent bonds, because we see an attractive force, but there's not enough electrons to give all the metals all the electrons they want, because the metals are just don't have enough electrons. And so because of that, these solids can have a wide range in melting points, depending on how well they pack and how many electrons they have. But these atoms are stabilized by a metallic bond. What a metallic bond is, we have these atoms present, and the electrons kind of delocalize their way between the atoms. It kind of spreads out, kind of like you popped a balloon full of water and it just kind of oozes out to all the other atoms. And these generates essentially a sea of floating electrons that stabilize themselves and all the neighboring atoms. It's like the sharing of the covalent electrons, but they're no longer localized into orbitals. They're now able to kind of like spread out to all the atoms around them. Now, because these electrons are not localized in orbitals, it means the atoms are not really stuck in bonds. And this means these atoms are very mobile, that these atoms can slip and slide and shear apart. And that's what gives them the property to be hammered into sheets. They're malleable. That they can be drawn into wires. They're ductile. That copper can be... You see some videos in the industry of them just like being pinched or sheared by just a big metal thing comes out and presses down and shears it off. Because the atoms are not held together very strongly, and so it's just a very easy break point. Also, having these sea of electrons helps them conduct electricity very easily, because the electrons need to jump from charge to charge, and so the sea of electrons really helps that. Because these guys have to be very tightly packed together, for the C electrons to work, they can also conduct heat very easily because they bump the energy of one atom is transferred to another atom, and they bump, and pass it down. Now, the hiccups. Now, most metallic solids will fit into one of those three basic shapes: the simple cubic, or the body-centered cubic, or the face-centered cubic. Now, if you were careful, you'll notice like the actual corner of those atoms, the corner of that lattice cell is in the center of the atom, and you'd be drawing a cube next to another cube next to another cube, so that the atoms that are in the corners aren't actually fully within the unit cell. They are only actually partially within the unit cell. But that's okay. That's okay, because even though the sphere is not fully in the cube, there is usually enough atoms so we count as one whole atom. So every corner actually only contains 1/8 of an atom. However, there are 8 corners. So essentially, every corner adds up to, say, there's one full atom within the cell. That if you stack this bottom cube next to, this guy would have to be 1, 2, 3, 4, and then 8 other cubes, was actually 7 other cubes that would add up to be one whole atom. Usually the whole atom being present. Now the atom in the center, because it's in the center, it's not on any of the faces, is present fully within the cell. Fully within the cell. And so that is 100% in the cube. So if you add up all the corner atoms, one atom, and the atom in the center, you're looking at a unit cell that contains 2 full atoms. And of course, the face-centered cubic, the atoms are cleaved in half by the face. So that means the cube that goes on top of this would contain the other 50% of this atom. The cube in front of this would contain the other 50% of this atom. So each atom in a face-centered cubic is only a half an atom, but since there are 6 faces, they add up to 3 atoms. And since there are 3 atoms from the face and 1 atom from the corner, we're looking at 4 total atoms. And each unit cell shows how these atoms pack within the crystal, and thus how other atoms can actually interact. That you'll notice that the hole right here between these atoms is very small, but there's a very large gap where these atoms come together. This hole right here between the 4 corners is a little bit bigger, but only because this atom is taking up space here. And so there's a little bit more space here, but no space directly in the center. So it's a smaller hole all in all. And these guys with the face-centered cubic even have even smaller holes. And so it depends on how atoms can interact with these guys. So with metals in mind, it is possible to have mixtures of one or more elements that give improved properties. This is referred to as an alloy. Alloys can fall into 4 major categories based on what's going on. So the first one is a substitutional alloy. That essentially most of these are mixed in at random, and it can make things a little confusing. But the lesser element in a substitutional alloy is randomly substituted within one of the other atoms. So instead of being a pure metal containing just lead structured in such and such a way, every so often we're intermixing a different element where lead would be. It is random, so you don't see a pattern of lead, tin, lead, tin, lead, tin, lead, tin. No, it's just lead, a bunch more lead, some tin, then a bunch more lead, and then some tin. It's like could be lead, tin, lead, 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 tin, tin, lead, tin, lead, lead, tin, and so the average works out to the same, but it's randomly and uniformly. So it's not just tin stuck at all one side, it's mostly lead and tin mixed throughout, replacing some of lead's spaces. And of course, the effect of how the size of tin compared to lead changes the properties, changes how it's packed. There's interstitial alloys. An interstitial alloy is where we have the lesser element fits into those little holes created by the close packing. This is typically done by nonmetals such as carbon. Carbon is added to steel, which improves the strength, that the carbon is able to bind to the iron atoms, help keep them together so that become harder and more brittle, but also harder and can hold shapes longer. But that's where they fit into the holes. There's heterogeneous alloys, where the alloy is not uniformly mixed, but it can be several parts, the mixed part and the pure base metal. Essentially, for example, galvanized steel, which we'll talk about at the end of the semester again, is an example of a heterogeneous alloy. You take steel and you dip it into zinc, and you get a thin little shell of zinc around the steel. And so it's not, zinc isn't mixed into the center, it's only coating the outside. And so near the surface between the two, there is some iron and zinc mixed together, but it's mostly iron core and zinc shell. And the final type is an intermetallic compound that is not randomly distributed, but actually has a set composition. So you would see an elemental structure and not like a percentage. It'd be like 3 coppers, 1 tin kind of thing. And it's like every 3 coppers there'd be a copper, tin, copper, copper, and so it's a set bonding. But here are some common alloys you might see. Wood's metal, which is largely bismuth, but it contains some amount of lead, 25% lead, 12.5% tin, 12.5% cadmium. And so these are this gives it a very low melting point. And this is used for like fuse plugs and automatic sprinklers. You have like a sprinkler that when the hot smoke allows it to melt, you have this water pressure that built up behind that's just going to pour through once this metal is melted. You have yellow brass, which is 67% copper, 33% zinc. That it's just nice because it's very ductile. You can draw that into like wires a lot easier, but it takes polish. They're very useful for hardware. Stainless steel, which is mostly iron, but small amount of interstitial carbon, and then amount of chromium and nickel that helps it reduce corrosion. The chromium and nickel changes its oxidative properties. Plumber's solder, which is the lead and zinc, lead and tin, which just gives it a much lower melting point, which we use for soldering joints. Sterling silver, which is silver with copper, which gives a brighter surface. And dental amalgam, which is silver, tin, copper, and mercury, which allows it to easily be worked to make up dental fillings. So, some of these are used in our everyday life still. Now, ionic solids are a little different. They tend to have a higher melting point, but because they have localized electrons that are stuck in the cation-anion pair, they tend to be a lot more brittle. and they don't conduct electricity in the solid form. They're more strongly held together, but because of that, when you hit them, they don't move, they just snap. They just shear at a weak point. Now, because of the positive negative, and you get some electrostatic repulsion between the positive and positive, we cannot have a simple closed packed shape. The atoms need to space themselves out so that the cations don't touch other cations, and the anions don't touch other anions. While one of the ions may adopt our simple cubic or body-centered cubic or face-centered cubic lattice, the other atom has to fit into that structure in such a way as to separate the charges, so we don't see that a cation touching another cation, that is always separated by an anion. Now, in this unit cell, we will see the cation-anion units matching up with that which we would typically call the molecular formula. So if I see sodium chloride as 1 sodium, 1 chloride, the total number of sodiums and the total number of chlorides in that unit cell must add up to 1 to 1. It could be 4 to 4, but it's the ratio of 1 to 1. So here are some simple ionic solids. We see cesium chloride. Whichever one you want to call cesium, one of them's in a simple cubic, and you have the other guy, probably the cesium, in the center in the body. And that it's how this is going to pack is keeping these chlorides far enough away from each other that they don't accidentally bump into each other. Now, sodium chloride, we see the chloride adopts a face-centered cubic. Face-centered cubic, where we have the chloride atoms in all the outer spots, so it's making up 4 different atoms, and the sodiums are adopting in the corners and one in the body. In the edges and one in the body. Each edge is 1/4 of an atom. So how many sets of edges are there? There are 3 sets of edges with 4 edges per set. So a total of 3 atoms. And one body makes 1 atom. So there's 4 sodiums and 4 chlorides, and they perfectly cancel out. Sodium fluoride adopts a very similar shape to sodium chloride. Magnesium fluoride is a little trickier. Magnesium adopts kind of instead of a usual cube, it's more of a rectangular shape. But we see here 1 magnesium in the body and 1 in all 4 corners, so a total of 2 atoms, all 8 corners. 2 fluorides in the body but off to the sides, and 4 fluorides in the face. So 1, 2, 3, 4. They simplify down to 2 atoms, and so 2 atoms and another 2 atoms, so a total of 4 atoms, 4 fluorides to 2 magnesiums, simplifies to 1 to 2. We have zinc selenide. It's called zinc blende crystal structure, but in this case, the zinc, I think the zinc is 4 atoms within the body, and the sulfur is a face-centered cubic, such that 4 body is perfectly matched by 4 edges, so it gets a 4 to 4 or 1 to 1. And this is just a crazy structure of scandium trifluoride, scandium 3 fluoride, where scandium is all on the edges and fluorides are all on the edge. Scandium's in all the corners and fluorides in all the edges. Now this is drawn, and all these are drawn in such a way that you can see the unit cell and you can see all the empty space. But in reality, these atoms will be much bigger and fill a lot of this space up, and there's not going to be all these big gaps in there. And so that all the sodiums are going to touch all the chlorides, all the zincs are going to touch all the sulfurs, and you won't see these guys bumping into each other in such a way. Now, molecular solids, we'll spend just a few minutes on this real quick. And that molecular solids are when we crystallize two distinct molecules of a given compound. Now, when this happens, you need two different things that's going to control this. Aspect one is the strength of the intermolecular forces. Greater forces means it's easier to occur. But the second thing is packing efficiency. How easily can they interact? It has to do with our surface, our surface area. If they can pack very easily and get a lot of intermolecular forces, it's a lot easier to stack them together and get a solid phase. So things with dipole forces and hydrogen bonds typically have a higher melting point. I mean, it's easier to freeze them. But molecular shape is another thing that greatly contributes. So, just for example, benzene is a C6H6 structure. It's a flat structure with double bonds, and so it has a nice pi cloud, and so it's essentially flat, and it stacks perfectly on top of other benzene molecules. So benzene freezes at 5 degrees C. Now toluene, its brother, has C7H8 structure, should have a higher boiling point because it has more atoms and thus more intermolecular forces. But because of this methyl group, the CH3, that is tetrahedral, it loses its perfectly flat stacking. Now, because of it loses that perfect stacking interaction, the melting point drops dramatically to negative 95 degrees C. So it doesn't want to stack as easily, and so it's a lot harder to freeze toluene for that reason. But we won't focus too much about molecular solids. The last type of solid are covalent network solids. They're very similar to molecular solids in that most of them are made up of nonmetals. But what is different is the covalent network solids are held together by specifically covalent bonds that run in a continuous repeating pattern. And we cannot separate them into individual molecules. Because of this, it imparts usually a very high strength and a very high melting point. So diamond structure, for example, is made up of all carbon, but carbons are in a tetrahedral pattern of sp3 hybridized carbons bound to 4 other carbons around them. When you look at the shape in a crystal structure, it forms essentially a zinc blend pattern that we saw in the ionic shape. The zinc blend shows up very often in covalent solids. However, carbon has several other allotropes, which are different versions of the elemental carbon. The other one, major one, is graphite, which is made up of flat layers of sp2 hybridized carbons that are all bound together by delocalized pi electrons. You can peel them apart. They have greater amounts of electron conductivity, but they're also very softer. So 2 ways to view diamond. We have our diamond. You can see the tetrahedral shape in each of these carbons. We've removed some of those carbons for clarity, but this is what it looks like, the zinc selenide, the zinc sulfide blend. There's graphite with its sp2 hybridized carbons in layers. and Buckminster fullerene, which is a C60 solid. It's just essentially a molecule. Silicon dioxide down here. The two ways of viewing silicon dioxide. But essentially that forms a zinc sulfide blend. The difference is the silicon dioxide, it kind of looks like the diamond, except that it has oxygens between each of these silicon atoms. And we have two different forms of boronitride. Boronitride can adopt a graphite-like shape and this strange little shape. But so there's some unique structures here, but we see some repeating patterns. Now, with that in mind, you might be asked about properties of atoms, or you might be asked to identify the molecular formula based on a unit cell. Now, please be careful. Sometimes the unit cell may include atoms that are outside the cell for clarity. Like this one, we have calcium fluorine coming together in a simple calcium fluoride molecule. If each calcium is green, it's trying to show you here that each calcium molecule is touching 8 other fluorine molecules. But it's also trying to help show you where they're at in respect cell. So the calcium is adopting a face-centered cubic. That is something you should be able to determine. It's not something that should trick you. So each corner is 1/8 of an atom. So 8 corners adds up to 1. Each face is 1/2 of an atom. And so each face, all 6 faces, adds up to 3 atoms. So how many calciums total are there? There are 4. Now here's the hard part, the fluorines. If you look at a crystal structure, it has a repeating pattern. You see, this fluorine is below the tops, but between these 2 faces. If I look at this fluorine right here, right, so this guy is in the body. He's in the body, but he's in the upper front right quadrant of the body. So these other 4 fluorines are in the respectively upper right back quadrant of the body, upper left back, upper left front. So we have 8 right here in the body. And we have another 1, 2, 3 hidden by this atom, 4, 8 on the back. Don't be a fool. Don't be fooled. These are a repeating pattern. 8 on top, 8 on bottom. That's partially why it shows you all these extra atoms. These 4 are outside the cell. They are looking at the 4 rightmost portions of the next unit cell. So there's 8 fluorines and 4 calciums. 4 and 8 simplifies to 1 and 2. So our unit cell is CaF2. Now we should have known that, because calcium is always 2+ and fluorine is usually 1-. However, the unit cell should have shown that. So that is the end of this chapter. Next chapter we will look at colligative properties, the properties of solutions. But I'll see you then.